Now,
this is the Laplace transform of t to the n e to the negative at ut, right? And I said that it was equal to n factorial over s plus a to the n plus 1. And as for the sine and cosine, the trick to perform the Laplace transform of sine and cosine is to break it into complex exponential functions. In the case of cosine, you're going to have to break it into e to the jbt plus e to the negative jbt over 2. And you take the Laplace transform of it, and then you use the linearity property of the Laplace transform. And once you do that, you're going to get this as the Laplace transform of cosine. As well as the sine. For the sine function, you break it into e to the jbt plus e to the negative. E to the jbt minus e to the negative jbt over j2. And you do the Laplace transform of each term, and then you combine them, and you're going to get this as a Laplace transform of sine. Now, b is usually the angular frequency of the sine function. So this is the b, the angular frequency. The last one.
so I think I should write it down here. Sine of bt ut, right? I think I should move it down here as the Laplace transform pair of b over s squared plus b squared and cosine of bt ut as the Laplace transform of s over s squared plus b squared. Now, another one that I think I forgot to mention is this property. I think I forgot to mention last time. When we multiply, where is that? Yeah, here. Frequency shifting, I forgot to mention from last time here. If we multiply a function of t by e to the negative at, that is, we're multiplying it with the complex. We're multiplying a function with an exponential function here.
See, suppose you want to take a Laplace transform of e to the negative at ft, right? Then the result would be the Laplace transform of f, and then replacing s with s plus a. Replacing s in the Laplace transform of f as s plus a. And then that is the Laplace transform of the whole thing here, of the product between the exponential and f.
So, that is called frequency shifting. In fact, the variable s there has a unit of radians per second. So that's why we call it frequency shifting, because s, the variable s, the unit of s is radians per second. So we're shifting s, so that's why we call it frequency shifting. All right, so if we do the frequency shifting over the sinusoidal, we see that we're gonna get e to the negative at cosine of bt ut. This will have the Laplace transform of here. Notice that I'm multiplying e to the negative at to cosine, right? So I know that in the s domain, I have to replace every time I see s with s plus a. So here multiplying with exponential corresponds to replacing s with s plus a. So this is the cosine. So I have to look at this guy, right? So I have to replace s with s plus a. So I'm gonna get s plus a in the numerator divided by s plus a squared in the denominator plus b squared. Okay, and as for the sine, it's the same, similarly. So e to the negative at and sine of bt ut has the Laplace transform pair of b over s plus a squared plus b squared. So I guess these are all the Laplace transform pairs that you should know. That's it. If you need to write something down on the A4 notes, then this table is a definite thing that you should write down. Okay? Any question? No. All right. Now, I would like to spend a couple of hours probably on inverse Laplace transforms. Now, I'm trying to write using a very neat handwriting. So I've switched from a pen, a ballpoint pen to fountain pen, so that I can focus on my handwriting and want to make it more beautiful. It's as good as I can get. The inverse Laplace transforms. Now, let's suppose that we have suppose we are given h of s, right? We would like to we want to find ht, okay, which is the inverse Laplace transform of hs. Okay, we're given hs. We're given the s domain function hs. We would like to find the time domain function, the corresponding time domain. How do we do that? Usually in engineering, all right. Usually in engineering, the hs that is given is in the form of rational function. Usually, almost 99%, almost 100%, almost always, h of s is in the form of the rational form, rational function. So what is a rational function? A rational function has this form, hs equal to some constant k, which is a real number, and s minus z1 times s minus z2, and so on, and then times s minus zm divided by s minus p1 times s minus p2 times s minus pmn. Okay, this is the rational form. It is a form that you will see almost always. This form. This is the rational form. Now we'll be focusing on this form only. We're not gonna do the inverse Laplace transform or some other forms. Just this form. Now, so what are the variables case z's, and p. Now k is a constant number. K is a real constant. Okay, for example, k is -3, k may be 1, k may be 10, k may be 10.2, k may be -3.2, so it is a real number, right? Now, z and z1 through zm are complex numbers. Okay, z1 through zm are complex numbers called zeros of h. So it has a name. Z1 and Z3, I'm sorry, 3, 1 through Zm have a name, and they're called zeros. The zeros of H. The reason why they're called zeros because if S has the value of Z, then the whole function reduces to 0. That's why they're called zeros. Okay, for example, if you plug in S as Z1, then the whole thing collapses to 0. So that's why they're called zeros. Oh, and keep in mind that they're complex numbers. Okay, they're complex numbers. That means that they have both the real part as well as the imaginary part. Okay, and for P1 through N, Pn, they're also complex number. And they have a name. They're called the poles of HS. Now the reason why they're called poles is because if you plug in S, for example, if you look at here, if you plug in S equal to P1, then the whole thing will become singularity. The whole thing will become infinite, right? So that's why we call it a pole. If you plug in S equal to P2, then it's gonna become an infinity. Then we're gonna, that's why we call it. They are singularities of the functions. They are the points that if you plug in, then HS will be undefined. Now, so here it is. Now we're gonna consider 3 cases. Okay, we're gonna consider 3 cases. The step is as follows. The step is steps. Given HS, break it, HS into something called partial fraction decomposition. Okay, and then the second step is to find the inverse Laplace transform of each term. Okay, and then add up to find HT. Now, in the first step, when we want to break it into partial fraction decomposition, so what do we mean here? We're going to have to consider 3 cases, right? Case 1. when all the poles are distinct. In other words, there are no repeated poles here. No poles are repeated. All the poles are distinct. All the poles are different. So in this case, this is a very easy case. It is probably the easiest case that you can find. Okay, so then we can write down the partial fraction decomposition becomes the decomposition that I'm talking about in this first step becomes when all the poles are distinct, the decomposition becomes Hs equal to K1 over S minus P1 plus K2 over S minus P2 plus blah 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 plus Kn over S minus Pn. Now, I would like you to compare these two. Sorry about, I have to shrink the screen. I would like you to compare between these terms, and the original h there. You see, the denominator of h, there are n terms in the denominator of h, right? N terms, starting from P1 through Pn, n terms. So because all poles are distinct, I can break it into n terms again. And the number of terms in the decomposition is equal to the number of terms in the denominator. Okay, for example, if there are 3 terms in the denominator, then this composition will have 3 terms, 1, 2, and 3. And the denominator of here is equal to one of the terms in the denominator of the original function. Now, K1, K2, and K3. Now, P1 through Pn may be a complex number. When there is a complex number P, then K, the corresponding K will also be a complex number. Okay, but in the first case, we're going to consider only real numbers. Now, the number K here can be determined quite easily using this formula. This is how to determine Ki. This is how to determine the numerator corresponding to S minus Pi. Now, for example, and then once we do the inverse Laplace transform, we'll get taking the inverse Laplace transform on both sides. The left-hand side would be ht, right? The left-hand side here, this is hf, right? So if you take the inverse Laplace transform, it becomes ht. Now on the right-hand side here, each term on the right-hand side is the exponential term. Remember this. Go back here. See, this is s plus a, right? 1 over s plus a corresponds to the e to the negative at ut, right? Keep this in your head. And then, this is
1 over s minus p1. So the inverse Laplace transform will be e to the p1 tut, right? So the first term, the inverse Laplace transform, the first term is k1 e to the p1 tut, right? And the inverse Laplace transform of the second term is k2 e to the p2 tut. And then the rest of the terms similar. So it is kn e to the pnt ut. So if you rearrange it, you will have this as your ph of t. So you see, we see that the poles in ht is just the exponent values, okay, in each of the exponential terms here. So this is the simplest case. This is the easiest case. Now let's do an example. An LTI system has the transfer function given by Hs equal to s plus 1 over s to the third minus 5 s to the second plus 6s. Okay. We would like to find the impulse response. Find the impulse response of the system. Find the impulse response of this system. Now, the question gives us the transfer function of the system. This is the transfer function. We know that the impulse response and the transfer function are related. The transfer function is the Laplace transform of the impulse response. So, given the transfer function, we can find the impulse response by taking the inverse Laplace transform of the transfer function. Right. Note first that the transfer function h, if you remember, is the Laplace transform of the impulse response. Ht. Okay, in other words, Hs is the Laplace transform of Ht. Okay, and so if you take the reverse path, right, the impulse response will be the inverse Laplace transform of the
transfer function. Now, the question gives us the transfer function, right? And it wants to find, it wants the impulse response. So what we have to do is just, we have to take the inverse Laplace transform of Hs. So, now, we first have to do rearrange Hs to find all the poles. Now, to find the poles, we have to decompose this denominator, right, into the product form. So, we have Hs, which is s plus 1 over s cubed plus minus 5s squared plus 6s, right? This is given from the problem. Okay, we're given this. And then we decompose the denominator into the product form. We're going to have s times s minus 2 times s minus 3. Okay? Now, please don't ask me how to go. Don't ask me how to go from here to there. You should be able to know it. You should be able to do it. Going from this to this, and yeah, please know it. Right? I can't teach you this. It's from high school. So the numerator is the same, doesn't change. So now we are in the rational form, right? This is in rational form. So can you locate the zeros at the poles? There is 1 0, right? There's 1 0, and that is negative 1. So 1 0, and that is z1 equal to negative 1. That is the only zero in Hs. How many poles are there? 3 poles, right? There are 3 poles. The first being 0. That is the first pole, right? We can always write this as s minus 0, right? S minus 0. So the first pole is 0. Now, what are the second and the third poles? The second pole is at 2, right? And the third pole is at 3. So the second pole, P2, is at 2, and the third pole, that last one, is at 3. So there are 3 poles. Now, usually we don't care about the zeros. Zeros do not determine the characteristics of the system. It is the poles that determine the characteristics of the system. So usually we don't care much about zeros. Okay, the things that we care most are the poles. So the poles are more important, much more important than zeros. Now, if you look at the poles that we have here, you see that there are 3 poles, and these are distinct. Nothing are equal, right? They are distinct poles. So since the poles are distinct, okay, the partial fraction decomposition of H is in this form. It's in this form. Okay, the poles are distinct, right? So this is the partial fraction decomposition. So we can decompose this into 3 terms, which is the number of poles, right? So the first term is K1 over S. The second term is K2 over S minus 2. And the third term is K3 over S minus 3. Okay? And now we have to find K1, K2, and K3. K1 is easy. It's S times HS. And then we plug in S equal to 0, which is the first pole. Now we have to find this, we have to go back to original H there. Okay, when we multiply it out by S, right? So the factor S in the denominator is gone. So we're left with, when we're multiplying this with S, this term is gone, right? So we're left with only this guy, right? And then once we know this, we plug in S equal to 0. So we're gonna get 1 over minus 2 times minus 3. That is 1 over 6. So we have 0 plus 1 divided by 0 minus 2 times 0 minus 3, and that is 1/6. Okay, and the rest is the same. K2 is S minus 2 HS, and then plug in S equal to 2. And that is 2 plus 1 divided by 2 times 2 minus 3. And that is 3 over minus 2. Okay, minus 3 over 2. And the last one, which is K3, is S minus 3 times HS. And then plug in S equal to 3, and we'll have 3 plus 1 divided by 3 times 3 minus 2. And so we have 3/4. I'm sorry, yeah, 4/3. Yeah, 4/3. Now, once we know all this, okay, once we know K1, K2, and K3, we can plug them back into HS. Right? We can plug it back into HS. So we have the partial fraction decomposition already, which is HS equal to 1/6 over S minus 3/2 over S minus 2 and plus 4/3 over S minus 3. Now, we can do the inverse Laplace transform, which is HT. That is the inverse Laplace transform of HS, right? And so it is equal to the inverse Laplace transform of each term added together. So 1/6 inverse Laplace transform of 1 over S minus 3/2 inverse Laplace transform of 1 over S minus 2, and then plus 4/3 inverse Laplace transform of 1 over S minus 3. You know, in my opinion, this is the easiest part in this course. This is very easy. It is probably, I think, it's the easiest section in this course, and everybody should get some points out of this. So the inverse Laplace transform of 1 over S is ut, right? And the inverse Laplace transform of 1 over S minus 2 is e to the 2t ut, right? And the inverse Laplace transform of 1 over S minus 3 is e to the 3t ut. So group them together, you're gonna get 1/6 minus 3/2 e to the 2t plus 4/3 e to the 3t, right? And then ut. That's it. Okay. So this is the answer to this question. This is the impulse response of this system. Easy? Doable? Now, that was the first case. That was case one where the poles are distinct, right? This is case one. Now, in the second case, we're going to consider that in the case where some poles are repeated. So the case number two, some poles are repeated. Let's see, sorry. Yeah. Some poles are repeated. So in other words, the function hs is in this form. Some numerator, okay, some numerator will actually, sorry, um, um, k is minus z1 times s minus zm. This is the zero section and divided by the poles. Now, s minus p1 times s minus p2 to the r. Here.
Yeah. To the R. So how many zeros are there? There are m zeros, as in the previous case, right? There are m zeros, but how many poles are there? There are r plus 1 poles. Okay, out of r plus 1 poles, the last r poles are repeated.
Here, so let me write it down. So in this case, there are m zeros, okay, and the zeros are z1 to zm. Okay, these are the zeros. Now, there are r plus 1 poles. Not 2 poles, but r plus 1 poles, all right? Not 2, r plus 1. The number of poles is determined by the number of terms here. There are r plus 1 terms, right? So there are r plus 1 poles. And these r plus 1 poles are p1, p2, p2, and then p2 again, right? But because p2 are repeated, are terms. So these are our poles, okay? So these are our poles here, r plus 1 poles. So p2 are repeated, so p2 is repeated r times. Now, when this happens, you cannot use this formula to do the partial fraction decomposition. This formula is not valid anymore. If there are repeated poles, then you cannot use this formula because you're going to see that this will be the same, right? This will be the same, and you will go nowhere. So what you do is you're going to write down r plus 1 terms, okay? So the partial fraction decomposition becomes is now hs. Look here, look carefully. For the poles that are not repeated, in this example, it's just p1, right? In this case, it's p1. If you have unrepeated pole, then things are as it was. So we're going to have k1 over s minus p1. Now, because p1 is distinct from the rest, right? So you can just write it down as if it was in the first case. Now, as for the repeated poles, what you do is you're gonna write down the terms. You're gonna write down R terms, which is the same number as the number of the repeated poles, right? Because there are R repeated poles, so you're gonna have R terms. The first term is K2 over S minus P2. The second term is this K3 over S minus P2, and then you have to square it. You have to put a little 2 here in the exponent term here. S minus P2 to the second. And the third term is K4 over S minus P2 to the third. And then you add it repeatedly until you find the last term, which is K R plus 2, right? K R plus 1 over S minus P2 to the R. And this will be your partial fraction decomposition in this case, when there are repeated poles. Oh. Now, to determine K's, okay, K1 for poles that are non-repeated. In this case, it is P1. You can determine K pretty easily by multiplying S minus P1 to HS and then plug in S equal to P1. Right? Now, if there are 3 non-repeated poles, then you have to do this 3 times. 1 for each of the non-repeated poles. Now, to determine K2 through KR plus 1. Oh, by the way, KR plus 1 is quite easy. But actually, yeah. Also, we can find the last term of the repeated poles straightforwardly. Okay, that is the last term, right? KR plus 1 is equal to S minus P2 to the R plus 1 times HS. And then S is equal to P2. Now, unfortunately, for K2 to KR, you cannot use this formula. You have to differentiate it with respect to R first. With respect to S first, and then you go from there. But we're not gonna go to use that approach. We're not gonna take derivative because I think it is by taking derivative it is quite messy. So I'm gonna choose a different strategy here. For K2 until KR, we need to do some algebra and compare the coefficients. Okay, and I think the best way to know this is to look at an example. So I'm gonna give you another example. Now, suppose the transfer function and LTI system has the transfer function equal to uh, s over s plus 1 times s plus 2 squared. Okay, we want to find ht, the impulse response. We want to find the impulse response from this transfer function. So basically, what you need to do is we need to find the inverse Laplace transform of the transfer function, right? So that is what we need to do. Now, so looking at Hs, we see how many zeros are there? How many poles are there? We see there is 1 0, and that 0 is at 0, right? Because the numerator is s minus 0, and so the only 0 is at 0. And how many poles are there? 3 poles, right? There are 3 poles. The first being at -1. The second pole and the third pole are equal, which is at -2. Okay? Yeah, at -2. So these 2 poles are repeated 2 times. They're repeated. It is repeated 2 times. So because we have repeated poles, right? So the partial fraction decomposition of this function becomes now -1. The first pole is not repeated. P1 is not repeated, so you can use this formula to write down the first decomposition, which is s plus 1, right? S plus 1. Now, for the second and third pole, okay, they are repeated. So you have to still add 2 terms. The number of terms to add is equal to the number of repeated poles, which in this case, 2 terms. So you have to add 2 terms. The first term and the second term. Now the first term, you just copy s plus 2. Okay, right to here. But the third term, to make it distinct from the first term, you have to square it. If you don't square it, then they will be the same, right? And you will go nowhere. So you have to square it 1 time. So this is going to be the partial fraction decomposition of this function. And now we need to find k1, k2, and k3, right? For k1, it is straightforward because this term belongs to the non-repeated pole. So k1 would be s plus 1 times hs. And then plug in s equal to -1. Okay? And so we have -1 over -1 plus 2 squared. Look at hs here. Look at hs here. When we multiply it by s plus 1, it means that we are eliminating. We're kicking this out of the equation, right? And then we plug in s equal to the -1. We're gonna get this. So we have -1. Now k3 is easy. K3 is s plus 2 squared times hs. And then plug in s is equal to -2. So we have -2 in the numerator divided by -2 plus 1. Okay, so it is 2. Now, K3 is 2. Now, K2 is more involved. You cannot multiply HS by S plus 2 to find K2. It would not work that way because if you think that you would multiply this thing by S plus 2, if you do this, you still have the denominator left, right? Which is S plus 2. And then when you plug in S equal to -2, it will collapse. You will go nowhere. So you cannot do that. Now, so to find K2, you need to plug these two guys back into the original equation and then do some algebra. So to find K2, we plug K1 and K3 back into HS. Okay, and when you do that, you're gonna have HS equal to -1 over S plus 1 plus K2 over S plus 2 plus 2 over S plus 2 squared. Yeah. What I did was just I plugged in K1 and K2 here that we found back to this equation and then get this equation. And then we need to do some algebra, right? So we have to combine them. When we combine them, we get S plus 1 times S plus 2 squared, right? And then the first term is S plus 2 squared. The second term is K2 times S plus 1, S plus 2, and the last term is plus 2 times S plus 1. Okay, and then the first is the perfect square, right? So minus S squared minus 4S minus 4. The second term is plus K2 S squared plus 3K2S plus 2K2. And the last one is 2S plus 2 divided by S plus 1 times S plus 2 squared. Okay. And then we group them. Okay, we group them according to the S term. The first term is S squared, right? So we group them. How many terms are there? We're going to have two terms. The first being -1 plus 3K2. Okay, because we have two S squared terms. The first is minus S squared and the second term is K2S squared, right? So we group them. We're going to get -1 plus K2, only K2. Now, as for the second term, the degree of S is 1, so we have -4. We have 3K2, and we have 2. Okay, add them, we get -2 plus 3K2, right? Times S. And then the degree 0 term is -4, 2K2, and 2. So we have -2 plus 2K2. And divided by S plus 1 times S plus 1 squared. S plus 2 squared, sorry. Now, but we know H is equal to S over S plus 1 times S plus 2 squared, right? And that is, if I rewrite it quite naively, I'm going to get 0 times S squared plus 1 times S plus 0, right? divided by s plus 1 times s plus 2 squared. So what you see here,
both of them have to be equal, right? They both have to be equal. Now, to make them equal, for them to be equal, you see this term has to be 0. You have to compare terms. This guy would have to be 0, right? For them to be equal. This guy would have to be 1, and this guy would have to be 0. Now, the only way that makes it possible is that k2 is equal to 1. When k2 is 1, you see the last term is 0, the second term is 1, and the first term is also 0.
so when you compare the coefficients, you see that k2 is 1. Comparing coefficient, we have k2 equal to 1. Now, you may have a question, okay? If you have the third term, if you look at the third term and you get k2 equal to 1, but for some reason the second term makes k2 equal to 0. Is that possible? That would not be possible, right? It means that there is a mistake somewhere. If you got that, if you got into that situation, let me say it again. If for some reason you look at the third term, this coefficient, the third term makes you k2 equal to 1. But for some reason, the second term gives you k2 equal to -1. So there's some inconsistency, right, out of this. When that happens, it means that there is some mistake somewhere above. So you have to go back and find those mistakes because it is not correct. They have to be consistent with each other. If the third term gives you k2 equal to 1, then the second and the first term would also have to give you k2 equal to 1 as well. Okay, you see what I'm saying? They have to be consistent with each other, which I am lucky that they're consistent. So that means that there shouldn't be any mistakes previously. So now we have k2 equal to 1, so which means that we have hs equal to -1 over s plus 1 plus 2 over s plus 2, and the last one is plus 2, right? Plus 2 over s plus 2 squared. Now, at this point, if you have time and you have nothing else to do, okay, instead of falling asleep, you may combine them. Okay, you may combine them and see if you get this one back or not. If you combine these terms, the three terms, you should get this one back. If you don't get this one back, it means that it is not correct. Okay, because they have to be equal. They have to be the same. We are decomposing this thing into these three terms. So they have to be the same. You combine them. If you don't have anything else to do in the exam, right? Now, from here, we're happy because we can find the inverse Laplace transform with each term, right? The first term gives us e to the negative tut, right? Okay, yeah. Oh, it is 1, sorry. Thank you, it is 1. Thank you. The second term is e to the negative 2tut, right? And the third term is 2t e to the negative 2tut. Now,
the t here, okay, the t here comes from, we have a second order exponent here. So that
I'm using this formula. T 1 over s plus a to the n plus 1 is paired with c to the n over n factorial.
So I use this formula to get this guy. We see that A is equal to 2, right? A is equal to 2, so e to the negative 2t. And n here is equal to 1, right? So I have 1 factorial, which is t to the 1, t to the first over 1 factorial.
So putting them together, the impulse response of the system would be e to the negative t plus 2t plus 1, or minus here, e to the negative 2t, and then ut. That is the answer. Okay?
That should be the answer.
I almost forgot the negative sign there. The first term. Almost. Okay. Any question so far? Straightforward, right? You know, just get your hands dirty by doing some algebra. And then you should have to remember anything. Forgot to put mask on. All right, now the third case. Oh, by the way, think about this. What if now let's look at this case. Hs is equal to S over. Let's make it more difficult, but we're not gonna do it, all right? Because it's gonna take some time to complete all of it, which we don't have. So we have. Suppose we have S plus 1, S plus 2, S plus 3, S plus 4 to the second, and then S plus 5 to the third. So how would you go about doing it, this case? I've made it unreal, actually, but to illustrate some points. Now, how many poles are there? How many zeros are there? There's just 1 0, right? 1 0. We're not going to do this, all right? I'm just going to start it for you. Just 1 0, and that is 0, okay? Because we could write it as S minus 0, right? And that 0 is 0. Okay. Now, how many poles are there? I'm counting. What's it? I'm counting 1, okay? 1, 2, 3, 4, 5, 6, 7, 8 poles. So there are 8 poles, right? 8 poles altogether. 8 poles. Okay, P1 is minus 1, P2 is minus 2, and P3 is minus 3. So these are non-repeated poles because they are not repeated, they're distinct. And the rest, another 2 are repeated 2 times. So P4 is equal to P5, which is negative 4. And the rest 3, P6, P7, and P8 are equal to negative 5. So these are all the poles in this function. So because there are repeated poles, so the partial fraction decomposition would have to be Hs. For the non-repeated poles, things are simple, right? Life's simple. So we have K1 over S plus 1 plus K2 over S plus 2 plus K3 over s plus 3, right? And now for P4 and P5, you have to write it as this. K4 over s plus 4 plus K5 over s plus 4 squared. Okay, and the rest, 3 terms plus K6 over s plus 5 plus K7 over s plus 5 squared, and then plus K8 over s plus 5 cubed. Here. You see, ultimately, we're going to have 8 terms as in the number of poles. Okay, because there are 8 poles, right? So we have 8 terms. We're going to have 8 terms. Now, these three terms, these two are the 2 times repeated poles. And these 3 are the 3 times repeated poles. Okay? And these are individual poles. Okay, so we have here. These are distinct. These are distinct. This belongs to the 2 times repeated, and this belongs to the 3 times repeated. So to find K1, K2, and K3, it's quite easy, right? K1 is s plus 1 times h, and then plug in s equal to the minus 1, and blah blah blah, as well as K2 and K3. Same, right? Similar approach. Now for K5 and K8, it's easy as well. K5 is s plus 4 to the second hs, and then plug in s equal to negative 4, and K8 is s plus 5 cubed hs, and then plug in s equal to the negative 5. Now, you have to get your hands dirty again when you want to find K4, K6, and K7. Okay, so plug in all this back to KH to find K4, K6, and K7. So ultimately, when you find the inverse Laplace transform, you're going to get K1 e to the negative t plus K2 e to the negative 2t plus K3 e to the negative 3t, okay? Plus K4 e to the negative 4t plus K5t e to the negative 4t. Actually, I could have written K4 plus K5t plus K6 over 2 t squared. Sorry, only 2 terms. Here. E to the negative 4t and plus K6 plus K7t plus K8t squared over 2 e to the negative 5t, and then multiply the whole thing by ut. So this is the inverse Laplace transform of that function. So your job is to find K4, K6, and K7 to plug into this. K4, K6, and K7. Right? I'm not going to do it. Okay, you can do it. Not so hard, but you know. Okay. Any question? No. Now the last case, which is case number 3. Okay, case number 3 is when there are some poles, there are some complex poles. So if you notice up to this point, no poles are complex numbers. But when there are complex poles, okay, you have to consider case number 3. There are some complex poles. This is the third case. Some poles are complex numbers. Now, fact is there is a fact from algebra. Okay, if you learn algebra, you're gonna have to prove this fact. The algebra states that if all the coefficients of Hs is real, if all the coefficients of Hs are real number. Sorry. Fact. Well, I'm just saying if there is a pole that is a complex number. By complex number, I mean there is the imaginary part. The imaginary part is not equal to 0. That is what I mean by complex number. If there is a pole that is a complex number, then there must be another pole. Then there must be another pole. Okay, there must be another pole that is the complex conjugate of that pole. Well, let's say that this pole is pi. Okay, so there must be another pole that is the conjugate of pi. So in other words, complex poles come in complex conjugate pairs. Okay, come in pairs. Complex poles come in conjugate pairs. Now, so if you have a complex poles, okay, complex conjugate pairs will be this thing, right? So how to find the inverse of Laplace transform when you have a complex pole? There are several methods to tackle this problem, but as far as I'm concerned, I think the easiest method is to do the algebra approach. So I'm gonna illustrate that to you. So let's gonna do some example. Let Hs equal to let's see. For S plus 25, 29, for 29, S plus 1 over S times S squared plus 4S plus 29. Okay. Oh, almost time, right? So we're gonna leave with this example then. Okay? We're gonna do this example, complete this one next time. And we're gonna finish, I think we can finish the Laplace transform next time. After which we'll start Fourier series. And after Fourier series is done, then we can take the short exam as promised. So I think we'll leave here, and then next time we'll try to find this inverse of Laplace transform.
Again, if you don't know your score yet, you can send me an email and I can reply you with your score. If you don't send me an email, I won't know your email address. I can't send you the score to you. All right? If you don't know the score yet, the midterm score, send me an email. If you get a very, very low midterm score, I think my recommendation is for you to drop the course. For example, if you get 0, you should definitely drop the course and take another chance next term. So as for the attendance check, yeah, right. This time I don't forget. So check attendance and then Google Form sign in. I have to activate it for you guys. Oh, it's been already activated already. So this time let's make it a B boy. It's been activated already. B boy. B. It's a B. B. It's a B. Okay, and see you guys on Thursday. Don't miss the class on Thursday because we're gonna finish Laplace Transforms, and then we should be able to start pretty series this Friday. ก็ไม่ต้องสอบเดี๋ยวไปคิดคะแนนทั้งที่เหลือแล้วก็คูณสัดส่วนไปเป็นร้อยเข้าใจอยู่ใช่ไหมเข้าใจนะสวัสดีครับใครไม่เข้าใจอะไรก็มาถามนะครับบทนี้เป็นบทที่เราจะได้คะแนนได้มากที่สุดแล้วนะครับผมบอกให้หลังจากบทนี้ไปอย่าหวังว่าจะได้คะแนนง่ายทั้งบทนี้นะครับจะยากเพราะฉะนั้นใครไม่เข้าใจหรืออะไรก็ตามถามได้ดีบอยฮะเดี๋ยวนะใส่ได้กับใส่แล้วการหาตัวเคมันหายตัวไหนตัวเคยังไงนะเขียนนะลิสติ้งไหมโดยสั่งลิสติ้งอันนี้คือ HS ใช่ป่ะดูนะถ้าผม multiply ทั้งสองข้างไป S plus 1ใช่ป่ะผมจะได้ K 1ใช่ป่ะได้ K 2 S plus 1ใช่ไหมครับใช่ไหมครับอย่างนี้ใช่ไหมแล้วผม multiply ทั้งสองข้างไปเสร็จแล้วผมแทน S ด้วยสูงแทน S ด้วย S ด้วยให้เลือกลบ1ใช่ป่ะตอนนี้ก็จะไม่ใช่ไม่เหลือตอนนี้มันจะเข้าใจยังเหมือนย้ายข้ามสมการไม่ได้ย้ายข้ามอะไรเนี่ยผม multiply ผมนี่คือ decomposition ผมใช่ป่ะหาแค่1ผลงานผม multiply s plus 1เพื่อจะกำจัดตรงนี้ไปใช่ป่ะที่เหลือมันก็ถ้าผมแทน s บวก1บวก1ไปมันก็จะกลายเป็นมันต้องทำบวกสมการเนี่ยนี่คือสายมันอะไรนี่คือเหตุคือเหมือนเอา s บวก1เท่ากับ0แล้วก็ s เท่ากับลบ1มา2ก็เพื่อนเข้าใจนะอธิบายต้องเพื่อนไม่เข้าใจว่าทำไมคือเอา s บวก1ทำผ่านแล้วก็ถ้าอย่าง s บวก1ก็คือตลอดเพราะเราอยากหาก็เนี่ยเพราะว่าถ้าคือแล้วตรงนี้มันตัดออกมาเกิดแค่ตัวเดียวแล้วที่เหลือก็เป็นอย่างนี้ใช่ป่ะผมแทนด้วย s ลบ1เข้าไปใช่ป่ะโทษแทน s ลบ1ตัวนี้ก็จะหายไปหมดเลยใช่ป่ะจะมีกี่เทอมก็จะหายก็จะเหลือฟอร์มูลาคือ k ใช่ยัง
เกิดรีพีทเสร็จถ้าเป็นอย่างนี้ล่ะถ้าเป็นอย่างนี้ปุ๊บมันต้องเป็น3 เทอมใช่ป่ะ k1 ส่วน s บวกไอตัว k1 กับ k3 ก็ทำเหมือนเดิมใช่ไหมจะหา k1 ก็คูณด้วย s บวก1ใช่ป่ะมันก็เหมือนเดิมใช่ไหมแล้วประธาน s ลบ1ก็จะหายหมดเลยใช่ป่ะถ้าหาตัวนี้ก็คูณด้วย s บวก2สแควร์ใช่ป่ะก็จะหายหมดเลยถ้าการ s ลบ2แต่ตัวนี้มันจะยากถ้าจะหาตัวนี้มันจะมีหลายวิธีแต่วิธีที่ผมทำให้ดูก็คือวิธีที่แทน k1 k3 เข้าไปก่อนแล้วก็บวกเทอมแล้วก็เทียบสมประสิทธิ์จะง่ายที่สุดเพราะว่าตัวเลขชุดนี้มาอย่างนี้นี่เลยมาจากนี้มาจากแล้วถ้าทานเข้าไปนี่สิต้องลองทำดูถ้าไม่ลองทำดูมันจะแต่จริงๆถ้าลองทำดูจะโอ้โหง่ายขนาดนี้เลยง่ายสุดแล้วได้ขนาดนี้เอาจริงลองทำดูเข้าใจนะโอเคนะลองทำดูก่อนสวัสดีครับ